am ready when all of it is ready. Okay. Start?
Yes,
Okay.
go ahead.
Thank you, Andre. I know in the last talk, we got 20 minutes. This will not take 20 minutes. This is going to be short. My topic here has to do with M31 and M33. Now, I could probably spend hours talking about RLIREs in these two galaxies, but I'm not going to do that. I'm going to focus on one specific application that I've been following up in the past year or so, which is using the RLIREs in these two galaxies to investigate the relative distance between them. M31's in front, M33's behind, but how far? What is the actual line of sight distance between the two galaxies? That's what we're going to talk about here. Now, in many talks about RLIREs, I refer to them as a Swiss Army knife of astronomy because they're just so useful in so many different ways. You already see many of these, during today's presentations. If you find one, it's got to be old. And by old, we mean usually 10 gigayears or older. If you find one and know its period and amplitude, you can measure its metallicity, at least a rough estimate for it. They're good standard candles, which established for a long time. And as we saw earlier with Sturge's method, they're also useful for getting reddenings, line of sight reddenings to the stars themselves. So here's the two galaxies we're looking at, M31 over there on the upper right, and M33. And I just kind of tilted the image so that it's right, north, and east. And they're important because there's been a lot of studies looking at low surface brightness structures around these two galaxies and connecting them, in the sky. And this is just one example of one of these maps from McConaughey et al. In 2018. So, just looking at it just with your eye, you can tell that there's bridges and filaments and substructures of stars coming off of M31, and then of course M33. And this has led many groups to think about, well, are these two galaxies interacting? And if they are, how do we model dynamically that interaction? And well, one of the inputs into the interaction is their distance, the distance between them. So this is just a screenshot of one of the animations that I took off the web from YouTube about how Alan's group has been modeling these interactions. So here's M31 here. This is the projected orbit of M33 around M31, several gigayears, in time scale. But obviously an input into these models is the relative distance of these two galaxies from each other. And so what I want to do is use the RLIREs in these two galaxies to measure that as differentially and as purely, differentially as possible. So the procedure is this. We have about 10 or so studies of RLIREs in these two galaxies, all of them with HST. There's one from the ground that we're not using. We want to be as differential as possible in this measurement. So we're looking at ACS observations in F606 of AB type RLIREs in each galaxy. We're going to adjust the Vega mag 0 point so that they're all internally consistent based on the recommended, space telescope 0 points. We're going to correct for the relative metal abundance using the Alcock relation. We're going to correct for the relative extinction using the Schlafly and Finkbeiner reddening maps. So this is only correcting the reddening in the Milky Way, not in the galaxy itself. We're going to just assume that averages out. And then after making those corrections, we're going to then compare the mean corrected F606 magnitude between the two galaxies in the fields that we've observed. So this is the equation. It's very simple. We take the published magnitude, subtract out the original 0 point that was used, add the correct Vega mag 0 point, which is a function of time. So that there's a website, there's like a whole Python script for that, and that'll calculate that for you. Do the correction for metallicity, extinction, and then here's the equation for the metallicity correction, and this is our correction. I'm sorry, the extinct. Yeah, this is the metallicity calculation, and this is the correction for the metallicity itself. We're going to just use the 0.23 slope, which a lot of people have used in the literature, and you can use 0.15, you can use whatever, it doesn't matter, as long as it's relatively the same between the two galaxies. So this is just a table showing you the various fields. There haven't been that many studies, like I said. Every single one of these studies, though, is largely based on archival data that wasn't intended originally for our RLIRE measurements. The only one really is this Jeffrey paper, which is based on Tom Brown's 120 orbit project observing Andromeda. All the rest are really observed for other purposes. And we just use the archival data because it had good time baseline to measure the photometry and the magnitudes and fit light curves and such. The thing to take away from this table is simply the studies that we've used and the different fields in each galaxy that those studies focused on. So here's what we're looking at here. Here's M31. Each field is these little squares. And of course, I used the same, just the name that was given to that field in those particular studies. This is from a paper that I did with Nahatai Tanakul. She got her PhD with me at University of Florida. She's now at the Research Institute for Astronomy in Thailand. So she was the first author. This was part of her thesis. So this is one of the fields in M31. Here's a few others that we've used. Now, some of these are so far out, there's really no or very few RLIREs in them, but there's one or two I don't use it. But if there's more than that, then I'll just take the mean magnitude of the RLIREs in those fields. And clearly, some of these are going to be influenced by the extinction in the galaxy, but I'm ignoring that for the moment, just assuming it's all going to average out. Here's some more images in M31, more fields. Here's M33. So we have these disk fields here, a couple of globular cluster fields, outer disk fields, and then two fields that are thought to be in the halo. We're not using these because these are ground-based fields, but all the rest is HST ACS observations. So here's the actual results. So we do all those corrections for the different fields. And in the vertical axis, we have the corrected magnitude. This is all the individual fields in M31 and M33. And taking in, finding the average, the weighted average of these two magnitudes, the difference is -0.3. Most literature values use -0.2. But this, I believe, is a more precise relative distance between the two galaxies. So that gives you, if you adopt 24.46, 115 kiloparsecs is the relative line of sight distance difference between the two galaxies. This was published in Monthly Notices last year. And then so I was looking for systematics. We have some, maybe there's a disk warp or a halo, deformity in the two galaxies. So I was looking for possible trends with position. So here's the plots of these magnitudes with right ascension and with declination. So M33 is over here, M31 is over there. I'm just looking for trends. Maybe one part of the of M31 is sort of tilted more toward M33 or something. And the only indication I could find was this point up here, with a very small error that might indicate. But if you take that point out, it makes no difference in the calculated distance. So I just kept it in the calculation. But clearly, there's a difference. The error bars are not overwhelming, and the resultant difference is statistically significant, and I believe the most highly, purely differential distance difference you can do. All right, so what I've been doing lately, working with Sevinch Gokman, who's sitting in the back row. She's a grad student at Florida Atlantic University. We're working on testing these two relationships for metallicity that Alcock came up with using period and amplitude, and I did with Andy Layden some years ago, just using period. So these two equations give you the calculated metallicity for each RLIRE using these properties of their light curves. And the question is one better than the other? So what I've been doing is going through and working with Sevinch, going through the galactic globular clusters. And let me just show this first. This is the table of globular clusters I could find with a decent number of RLIREs, with AB type RLIREs that have reasonably good photometry. And so there's 33 clusters, and this table will go in Sevinch's thesis and in a paper we're doing. But the point is that there's 33 clusters. They all have metallices in the Harris catalog. They have a decent number of RLIREs that we can use to do the calculation. So this is really what those relationships turn out to be. This is log of the period. This is amplitude. The solid lines are the Alcock relationships for -3, -2, and -1. And the vertical lines are the Sarajedini et al. Relationships for the same metallicity. So the Alcock relationship uses amplitude and period. The Sarajedini one just uses period. And really the question is, how much emphasis do you put on those two properties when you calculate the metallicity in each case? And what I'm looking to find out is one relation better than the other, or are they the same in terms of giving you the same population metallicity for a globular cluster. So here are the results. The vertical axis shows the difference between the Alcock and the Harris metallicity as a function of Harris. And this one here shows the difference between Sarajedini and Harris as a function of Harris. And this is the dashed line is the 0 line. And so what you see is, it's not 0. There's definitely a 0-point difference between the Harris scale and the Alcock scale in this case, and the Sarajedini scale in this case. And here's the plots, the same thing versus HB morphology. So this is the red HB over here. That's the blue. And this is red and blue. You don't see any obvious trends for the most part. At least I don't. The point here is just to show that what you see is an offset from 0 in the mean, in the metallicity of the clusters compared to the Harris catalog. And here's just the distributions. So here we have the Alcock minus Harris metallicities, Sarajedini minus Harris metallicities. The vertical line is 0, and I just fit a Gaussian. And the mean is just the measure of the difference in the scales of the metallicities. The important thing here is the standard deviation. The width of this is about 0.28. The width of that is about 0.28. It really makes no difference which one you use when you're looking at the mean metallicity of the populations. And at least in the case of Sarajedini, you only need the period. Here you need the period and the amplitude. So if you only have one number, then you just use the period and do a decent job in getting the mean of the population metallicity. All right, and then just want to show you. Okay, I was busy over the pandemic. Had an article published in Astronomy magazine about RLRE variables and their use in astronomy and stellar populations. That was in the July 2020 issue. I also worked on a podcast over the last 2 years called Astronomy Minute. It's available on Spotify, Apple Podcasts, and Google Podcasts. And basically and the reason why it's called Astronomy Minute is because every episode is not more than 2 minutes long. And the titles are things like, what is a star? What is a galaxy? What is a black hole? What is a pulsar? Really simple, very straightforward. And that's the website up there where you go to the website and there's 170 episodes, but they're all listed and organized topically on the website. You click on the link of the title and it goes to Spotify. You can go to Apple and Google too, but it's set up for Spotify right now. That was fun to do. I'm still adding episodes, but mostly it's done. And that's it. And then one last slide before this is the conference we did in 1995 with Heather. We organized this in Tucson. This was the 65th birthday, George, in 1995. And there, of course, is the proceedings that came out of that. So that was fun. That was the first conference I really organized with Heather's help, of course. We were a team, and it was a lot of fun. It was a good time also to get involved with that. So I will stop there and take your questions.
Two quick questions. Why should we still be using Harris's metallicities as fiducial?
Good question. Because they're based on the Coretta et al. Metallicity scale. What he went and did was he went back and collated all the metallicities for each cluster and transformed them all to the Coretta et al. Scale, which is I believe the latest accepted metallicity scale for globular clusters. So
when did those date?
2009, I think.
Okay.
Yeah, something like that.
For your differential distance modulus, did you attempt to try to see what the TRGB might give you as a differential?
So right. So that number of mine, minus 0.2, is a TRGB value. That's what most people have used.
Okay, so then why would the TRGB be wrong?
I didn't say it's wrong.
Well, it's different.
I said it's different. Yeah.
Yes.
I don't know.
They both can't be right.
True. I don't know. I think it's because my method, the method I presented here is as differential as you can get. The TRGB method, I'm not so sure. It's based on different people's photometry, different methods of measuring the TRGB, different ways of correcting for extinction. I mean, it's more heterogeneous, I would say, than just using the RLIREs this way.
Fair enough. Thank you.
So that raises the question, though. Are the RLIREs faint enough in the HST data that there's a Malmquist effect?
No. You mean, are they like, are
Close.
they so near the limit that
Yeah.
you're measuring them too bright or too faint? No, they're
Well,
I didn't show any of the color mag diagrams, but there are several magnitudes above the limit. So I think we're safe there, especially in the Jeffrey et al. Paper, which is based on the Brown 120 orbit project. There's plenty of signal to noise there to get good periods. The thing that I'd be concerned about would just be the qualification and categorization of the RLI as A, B, or C type. Sometimes there aren't enough data points to be sure that it's an AB type, and it might be qualified as a C type or it's AB. There's some confusion there, but that's really the only point that I would be concerned about. Like I said, most of the data in that table were not meant for RLIs. They were taken for other reasons, and we just mined the archive because there's enough data points to unequivocally, identify them as RLIs and measure their periods.
So what is the new updated relative distance between M31 and M33
The
mean?
new updated what?
This relative distance? Right, yeah, so what does it imply for the orbit of M33 and its interaction with M31?
Well, I don't know, because I don't do the modeling. So the folks that do the modeling will have to put that new relative distance into their models and run their code and see what like I said, the difference is 10 to a magnitude between what they were using and what this new value is. That's significant.
Yeah,
So-
and that's why,
Yeah,
I
so
thought it was
I don't
the-
know what that would mean. I presume if it's further away, then it's going to be harder to, attribute the interaction, I should say, the deformation of the galaxies to the interaction. There may have to be something else involved to give you the result, that we see in these sky plots.
thanks.
Regarding the Harris metallicities, I don't think they have metallicities in the Baumgart catalog of globular clusters, from what can I remember. So I think you have to use, I think the easiest way for a huge sample of metallicities would be to use Harris
Well,
for now.
You're right. I could go back and rederive the metal, well, not rederive, but calculate all the metallicities from scratch for each of those clusters. I could. I haven't done that, but I think
That's why
when
you're a graduate student.
when we go around to do the publication of sorry, I'm going too fast through these, but when we go around to publish these, we're going to have to make sure that all those Harris metallicities are on the exact same scale and as precise as they can be. But I chose Harris because it's the easiest, place to go, one place to go for all the abundances that I need.
What's the criterion to get into this table?
That there's enough RLIs, there's good observations, and by good, I decide whether it's good or not. There's enough AB RLIs to actually make an average. Now, some of these like 7, 5, 3, I'm not sure I'm going to choose select 3 RLIs. Is that enough? No. Right.
And you threw out omega sen because it's omega
Right.
sen.
Exactly. And even M54 is not on there.
Yes.
So, but I definitely don't have anything there with 2 RLIs. So I'm going to have to, I would go back, and Savinj and I would go back and work on this and say, all right, let's do the calculation, eliminating all clusters with less than 10, say, and then less than 20, and less than 30, and see if that makes a difference. I doubt it will, but it's a good test to do to check whether the small numbers are having an impact.
Yeah, really great.
Thank you.
I guess that's the end of the session, and see everyone tomorrow.
Not bad, 425.